The fourth project in grade 11 computer hardware is to make a Breadboard ATmega328P and have it run a unique circuit. Some of the parts that were necessary for this unique circuit are a single pole triple throw switch and a voltage regulator. The circuit that I chose to make was one that shows regular binary counting to 15, binary counting to 15 with the ones complement rule, and sign counting with the max of positive 7 and a minimum of negative 8. Another mini goal of this project was to make sure that the Breadboard ATmega328P could be run just by a 9-volt power supply. The only thing is, the ATmega328P and the shift register require exactly 5 volts, no more, no less. This is where the voltage regulator comes in. This regulator has 3 pins, the input, common, and output. It works by connecting the input pin to the 9-volt power supply, the common pin to the negative data lines of both power supplies, and the output pin to the new 5-volt power supply. This creates a circuit that takes 9 volts, converts 4 volts into heat energy, and lets 5 volts go into the power rails to power the breadboard. The circuit that I chose to make also requires the use of a single pole triple throw switch. This switch is relatively simple with one common pin connected to power, which can be connected to one of 3 options. The furthest left position is the left post pin, the middle position is the middle pin, and the furthest right position is the right pin. Computers show negative numbers using signed counting. Imagine if numbers were not infinitely linear, but if one counted for long enough, they would go back to where they started. In order to count negative numbers, computers can deem that at a certain number, it will start to count back towards 0. For example, when the computer reaches 127, all numbers after that are going to be negative, and the computer will count back to 0. So in this scenario, the unsigned binary value of 248 is equal to the signed value of negative 8. Finding the signed value of an unsigned number can be quickly done using the 2's complement rule. First, invert the bits, which is known as the 1's complement rule. Then, with the 2's complement rule, add 1 to that inverted value and the signed value has been obtained.